So in this video we're going to find the Laplace transform of these two expressions here. Log base 10 of 2x plus 5, log base 8 of 3x plus 2. So let's have a look at this one first. Log base 10 of 2x plus 5. Okay, now the way we can write this in terms of a natural logarithm, we can write that as ln of 2x plus 5 divided by log of the base, so the natural log of 10. So that's how we can write that in different format. Now we want to find the Laplace transform of that particular expression. Okay, now what we need first is the derivative of this. So let's take the derivative of this function here. So we let this function here equal f. So f equals ln of 2x plus 5 over ln of 10. Now the derivative of this, well, ln 10 is just a constant, so we've got 1 over ln of 10. And then the derivative of ln of 2x plus 5, that becomes 1 over the 2x plus 5. And then by the chain rule, we multiply by the derivative of 2x plus 5, which is just 2. So then that becomes a 2. So this is our derivative. So then that becomes 2 over ln of 10 times 2x plus 5. Now for this one here, so now log base 8 of 3x plus 2. Let's go through the same procedure of that, and then we'll bring them into Laplace transform together. So log base 8 of 3x plus 2. So we can rewrite that in terms of the natural log. That would be ln of 3x plus 2 divided by ln of 8. And again, as with this side, we're looking for the Laplace transform of that function. Okay, so now we'll set our function g this time to this interior one here. So g equals ln of 3x plus 2 over ln 8. And we need to find our derivative of g. So g prime, that equals, well, ln 8, same as here, that's a constant multiple. So ln of 8 goes straight in. And then we've got 3x plus 2 in our denominator. And then by the chain rule, we need to multiply all that by the derivative of the 3x plus 2. So then that just gives us 3. So that's our result for g prime and our f prime. Okay, so now we need the Laplace of these functions. Now the reason we took the derivative is our Laplace of a log function, that becomes, so let's put this down, Laplace of log based, let's call this a, bx plus c. Now what we need here now is the generic formula for that, which is minus 1 over t, and then the Laplace inverse transform of the derivative of this said function. So we'll call that the generic function. We'll just call that u prime of x. In this term, x is our variable. So that's our generic result for that. Okay, so now I'm going to clear these off the board, and then what we can do is we can then go with the inverse Laplace transform using this generic result of both terms. Okay, so there's the results on our board so far. So here, this one here was our function f, and this is our f prime. So now what we want to find is the Laplace of f. So using our generic formula here, we've got minus 1 over t, and then the inverse Laplace of the derivative. So we want the inverse Laplace of this. So 2 over ln 10 2x plus 5. Okay, now we've got a 2 here and ln 10 here. they can come out as constant multiples. So now we've got minus 2 over ln 10, and that's multiplied by t. And now we're left with 1 over 2x plus 5. So the inverse Laplace of 1 over 2x plus 5. Okay, now this one here, there's a generic formula we know for this one. We know that the inverse Laplace of 1 over x minus a, that equals e to the a t. That's our generic result for something similar to this. But we've got 2x plus 5. Here we've got an x minus some constant a. So this x needs to come down to a 1x. Well, here we've got a 2. So let's do some algebra on this. So now we've got minus 2 over t ln 10. And then the inverse Laplace of 1 over 2 times x plus, so divide that by 2. That would then get it into this kind of format. And then we've created another constant, which is a half. So this half again can come out. So now we've got minus 2 over 2t ln 10. Then x plus 5 over 2 in our denominator here. That would give us an a of minus 5 over 2. So then I can now write next to this our exponential function, e to the minus 5t over 2. So now I can rewrite this, with these 2's can now cancel out. So now I've got minus 1, so that's just a 1 there, so nothing else, t ln 10. And then e to the minus 5 over 2, minus 5t over 2, that will go in the denominator. So now I've got e to the 5t over 2 in my denominator. So that would be my result for this one here. Now let's go on and have a look at this one. Okay, let's take this off the board and we'll come back to that. So now onto my generic formula using my g. So Laplace of g, that equals minus 1 over t times the inverse Laplace of my derivative. So now here we've got 3 over ln of 8 times 3x plus 2. Okay, right, let's deal with that. So now 3x plus 2 will stay there. I'll have my 3 over ln 8. That can come out as a constant multiple. So now I've got minus 1 times 3, t times ln 8. And then all this is multiplied by the inverse Laplace of 1 over 3x plus 2. Okay, so as we had with this one before, we need to get this constant before the x taken out. So now we write this as minus 3 over t ln 8 times the inverse Laplace of 1 over 3 times x plus, now factor it out of 3, add 2/3. Okay, so now I've got another 1/3 to take out. So now I've got minus 3 over 3t ln 8 and times the inverse Laplace of 1 over x plus 2 over 3. Okay, so now we can deal with this one. That's going to be fine. X plus 2 over 3, very similar to how we dealt with this one. So then we get minus 3 over 3t ln 8 multiplied by e to the minus 2t over 3. Okay, so now we can rewrite this, cancelling out the 3's, not forgetting my minus sign of course. Now I can rewrite this now as minus 1 over t ln 8 e to the 2t over 3.